Gross geometry. This video series talks about the more wordy side of geometry, and let's get started with a bunch of dots. What conjecture can you make about the number of dots in the nth term? Now, conjecture is like, what true statement or fact can you make about what's going on here? Well, one term is one dot. Great. Two terms is 5. So 1 becomes 1, 2 becomes 5, 3 becomes, what is that, 11? Ugh, that's a terrible band. And 4 becomes 19. So what I immediately see is with 2, 3, and 4, it looks like I have 2 squared living here and I add 1. 3 squared, add 2. 4 squared, add 3. So that's how I'm going to approach it. I'm going to think my number term squared, and then I'm going to add the number less than that. So the way that we would show that is we would say plus n minus 1. But in order for that to be true, it has to be true for all. I didn't test that with 1 because, I can't really see that well with 1 as far as what I'm doing. But, if I do 2, it is 2 squared, 4, plus 2 minus 1, which is 1. So that works. So it works for you. 3 squared plus 2, 4 squared plus 3. This would be 1 squared plus 1 minus 1, which becomes 1 plus 0. So it does work. So we found our conjecture. So let's put this in a nice little statement. What conjecture can you make of the number of dots? There are n squared plus n minus 1 dots in the nth term. We'll write that there because I ran out of space. But yeah, that's what a conjecture means in this case. So this required us to think a little bit harder, and we did, and we got it right. Good job, everybody. Statement. All rectangles are squares. Provide a counterexample proving this statement is false. What is a counterexample? Well, a counterexample is a statement, a sentence that shows you and proves you that this statement is not 100% true. Okay, so like if I were to say, all cool guys are 23 years old, that's not true because I'm cool and I'm 28. So how can we do that here? How can we provide a counterexample for all rectangles are squares? Well, that's not true because some rectangles have sides that are not, there's an S there, all the same. For example, this guy, if I can draw correctly, is a rectangle. And these two guys are the same. These two guys are the same. That's a rectangle, but it's not a square. So basically, when you see a statement that says all or every or something like that, you're looking for a reason why that all or every is not true. And that's what a counterexample does. It shows you the lies, just like social media. Show that each conjecture is either true or false. So, all right, so I've got 2 statements here, and I need to show if the statement is a correct statement or not a correct statement. The sum of 2 even numbers is always even. So let's try a few out. 2 even numbers. 2 plus 6 is 8, even, check. 10 plus 16 equals 26, even, check. How about 2 plus negative 2 is 0, which is technically even, check. So it looks like no matter what 2 even numbers I add, it's going to be even no matter what. So is this a true statement? Yes, it is. That's a cat. Now, the product of two negative numbers is always negative. Is that true or false? Well, let's multiply two negative numbers together. Negative 3 times negative 4 is positive 12. Well, here it says the product of two negative numbers is always negative. Well, immediately I try one of them and it's false. So is this true? No, this is false. This says up here true or false, and I'm saying yes or no. I just wanted to say yes because I like saying yes. Like and subscribe. Identify the hypothesis and the conclusion of the conditional statement. A conditional statement says, if blah, 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 then blah, blah, blah. It could also be written like this, P then Q, where P is your hypothesis and Q is your conclusion. If P, then Q. This is already written to us as an if-then statement. So, fairly simple. The hypothesis is going to be the phrase after the if. So if a cat hears a cat opener or a can opener, I don't want to know what a cat opener is. If a cat hears a can opener, the conclusion is going to be the phrase following then. So then it will come running to the kitchen. So conclusion, it will come running to the kitchen. Okay? So conditional statement, if blah, then blah. After if is the hypothesis, after then is the conclusion. And it sure is easier when it's already written to us as a conditional statement like this one here. Cats. Write the following as a conditional statement. All right, a conditional statement is in this form, P then Q, which means if some type of hypothesis happens, then the conclusion. Okay, so if one thing, then the other. A plant will grow taller when it is watered properly. Now, we have to be careful here because we're not going to say if a plant will grow taller, then it is watered properly. That doesn't sound right. This is backwards. So our hypothesis is if a plant is watered properly. And again, the wording can be a little different, but since we're talking about plants, I want to make sure that I bring up the plant stuff first, then Q, then it will grow taller. Okay, so let's write that out. If a plant is watered properly, comma, and let's change colors, then it will grow taller. What's important with these is this is just how I'm writing it out. You may have a teacher, or you may have a friend, or you may have a deity that might write it out differently. But, this is how I'm wording it. And don't let the little words like, where should I put the word plant? You forgot to say the word when, why, blah, 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 blah. Don't worry about it. I'm just writing it out in a way that makes it sound like it makes sense. And the hypothesis comes first and the conclusion comes second. That's it. Write each. If a cat sees a laser pointer dot moving, then it will chase it. All right, so we have ourselves a conditional statement, which is in the form if P, then Q. P is my hypothesis. If a cat sees a laser point dot moving, that is P. It will chase it is my Q. What I have to do is turn all of these into the converse, the negation, the inverse, and the contrapositive. So let's start out with the converse, which is a brand of shoes. A converse says, let's just switch the Q into P. If Q, then P. We'll write that out in a little bit. Negation has you do P, then not Q. The inverse has you take the original but put nots in front of both of them. Speaking of converse, nots. And the contrapositive is you flip everything and make everything negative. So not Q implies not P. So let's do a little bit of writing. Converse. If a cat will chase it, then a laser pointer dot is moving. So I hate the way that that's worded, but that's it. If a cat, and let's actually be a little bit more specific. If a cat chases a laser pointer dot, if a cat chases a laser pointer dot, then it is moving. So what you saw me do here is I moved some words around to make the sentence make sense. If I were just to go in reverse and say, if it will chase it, then a cat sees a laser pointer dot moving. That's not wrong, but this just sounds better. If a cat chases a laser pointer dot, then it is moving. I'm kind of happy with that. Let's keep going though. Negation. So the first part doesn't change. If a cat sees a laser pointer dot moving, okay, so the first part didn't change at all, word for word, then it will not chase it. Then it will not chase it. So that's what that little squiggly means. That means we're going to take Q and make it a false statement or make it a not. There you have it. Inverse is we're going to write out the same thing but throw a not here and a not here. Oh, speaking of cats, one just walked into the room that I'm recording in. So hello, little kitten. No, please. I swear there's a cat here. All right. If a cat does not see a laser pointer dot moving, if a cat does not see a laser pointer dot moving, then it will not chase it. Okay? So P, thank you, not. Last but not least, we have our contrapositive, which is basically you rewrite out Q but throw nots in front of both of those. So if a cat does not chase a laser pointer dot, then it is not moving. So as you can see, these aren't fun. And the purpose of these videos or this series of videos, gross geometry, is there's really no math here at all. You're just making logical statements which will lead into something called proofs where you need to know a whole lot about logic and reasoning and all that stuff. And isn't that life? Cats and logic. That'll probably be the name of my memoir. Like and subscribe. Create a truth table for the conditional statement. If the Spartans win one more game, they will make the playoffs. So a truth table has you have your hypothesis, your conclusion, and then whether it's true or false based off of what you say. So there's only going to be 4 options here. Okay, both situations are true. The hypothesis is true, but the conclusion is false. The hypothesis is false and the conclusion is true. And if the hypothesis is false, then the conclusion is false. So when we look at this, we're going to view this from this real life fake problem that I just made. The Spartans win one more game is P. They will make the playoffs is going to be Q. So if the Spartans win one more game, they will make the playoffs. If the Spartans win one more game, they will make the playoffs. True. That's the original statement. So that would make sense that if P then Q, then P then Q is true. All right. If P is true and Q is false, if the Spartans win one more game, then they will not make the playoffs. Well, that is a lie given the original statement. If the Spartans win one more game, they will make the playoffs. So if someone were to come up to me and say, if the Spartans win one more game, they will not make the playoffs. Well, that's not true, according to this statement here. If the Spartans win one more game, no. If the Spartans win one more game, oh my gosh. If the Spartans do not win one more game, then they will make the playoffs. So basically, they can win no more games. They can win 2 more games. They can win 3 more games. They can win 4 more games. It all really depends. But since we are not given all the information, and I'm telling you right now that it's true that they will make the playoffs, then this statement is true, whether they win 1, 2, 3, 4, 0, whatever. If I'm running up to you and say the Spartans will make the playoffs, then it's true. Okay. So last but not least, true or false, if the Spartans do not win one more game, then they will not make the playoffs. That is a true statement. Okay? So there you have it. True, 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 true. I'm just repeating a Master P song from the early 2000s called True. Look it up. Just not in front of your parents. Lots of bad words. Write the biconditional statement for if lines intersect at 4 right angles, then the lines are perpendicular. Biconditional statements are if and only if statements. Okay, so I have children, and if my children are like, Dad, can we watch television? And if I were like, yeah, but only if you do your chores, then my children can watch television if and only if they do their chores. Well, lines intersect at 4 right angles. If that happens, then the lines are perpendicular. Okay, well, here's my if. So that's actually going to be my second part of the sentence. My first part of the sentence is lines are perpendicular if and only if they intersect at 4 right angles. So I know it sounds kind of backwardsy, but it all depends on if one depends on the other. Use the word depend a lot. But that's how this one works out. You got to kind of switch the words around a little bit, but I threw the if and only if. By the way, some teachers use this for if and only if, and if you're like, oh, that teacher doesn't know how to spell. No, a lot of teachers use that for if and only if. But those are biconditional statements. If. Law of detachment is one of those really weird rules. Basically, if I tell you that if P then Q is a true statement and P is true, then Q is true. Now, that's usually used when you have problems like this where not everything is as clear-cut as it could be, and so you're kind of going like, oh, we have to use logic now. That's what the law of detachment is. It's just logic. If Alicia scores 85 or greater on her test, she will earn an A on her final grade. Terrific. Alicia scores 89 on her test. What can you logically conclude? Well, if she scores 85 or higher, she gets an A. What did she score? 89? Oh, well then what can we conclude? She will earn an A, make it a big A, as her final grade. So law of detachment, kind of stupid. That's why this is called gross geometry, because gross geometry is kind of stupid. But, logical. So there you have it. The law of syllogism. There's nothing funny about the law of syllogism. Law of syllogism says if P then Q, and then Q then R, then P then R. Skips out the middleman. All right. If I am cool and if someone is cool deserves you to like and subscribe to my channel, then I deserve for you to like and subscribe to my channel. Law of syllogism. If it rains, then the ground gets wet. Neat. If the ground gets wet, then the grass becomes green. Neat. Using the law of syllogism, what can you conclude? Well, if it rains, that's P. Q is going to be the ground gets wet. The second statement starts out with if the ground gets wet. So what we're going to do is cut out the middleman and go right from P to R. If it rains, then the grass becomes green. If it rains, then the grass becomes green. And look at that. I chose a green pen just for this. I did it on purpose. All right, so this is the end of part 1 of gross geometry, where we aren't really doing a whole lot of math. We're doing a lot of logic. And logic is required for stuff that we will deal with called proofs, and that'll be the next volume of my gross geometry series. Thanks for watching. Welcome, ladles and jelly spoons, to an introduction to two-column proofs. What's a two-column proof, you ask? Well, I give you some information, probably a picture. I ask you to go from this thing to that thing, and I write out a two-column proof where I write out statements and reasons showing why this is allowed to become that. Think of the statements as you're solving a two-step equation, right? And along the way, you show your work and you're just kind of whittling your way down, blah-de-blah-de-blah-de-blah-de-blah-de-blah. Well, the statements on the left side are basically the work that you show. Now, what I would do is I would say, subtraction property of inequality, division property of inequality. Those are my reasons. So a two-column proof, and I'm going to quick clear this out, a two-column proof has me list all of the work that I would show to get from my given to my prove, and my reasons would be all the theorems and the postulates and the blahs that I know that have this make sense. Now, since this is an introduction to two-column proofs, I'm giving you all the statements, and it's my job to come up with the reasons. So, whenever you have a two-column proof, 99.9% of the time, your first statement and reason is going to be your given. Write that out. If this was completely blank, you would always start out with AC equals AB plus AB, and my reason is because that's the thing that you gave me, dummy. Step 1, finished. Step 2 says AB plus BC equals AC. Now, I have to look at this information and try to be like, okay, well, where did I get that? Did I get that from up here? No, I didn't. Let's look at my picture, AB. Oh, there's AB. So that matches up with that. BC, there's BC. So that matches up with that. And oh, yeah, I guess it would make sense that if I added those together, I would get AC, which is the whole thing. Now, whenever I take two or more segments and add them together to get a bigger segment, that's called the segment addition postulate. Let's write that out. Segment addition postulate. One more time, whenever you have to add segments, 2 or more, to get a larger segment, it's called the segment addition postulate. Similarly, when you do proofs, when you do the same thing with angles, it's called the angle addition postulate. So if like angle 1 plus angle 2 equals angle blah, 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 angle addition postulate, that's step 2, we're done. Now they went from AB plus BC equals AC, and they turned that into AB plus AB equals AB plus BC. What gives them the right to do that? Well, usually, not every time, but very often, a step or a statement comes from a combination of 2 previous statements. This is what I notice, that AC is AB plus AB. AC also happens to be AB plus BC. So if AC is this and AC is that, then this equals that. All I'm doing is I'm saying since AC equals AB plus AB, there you are, and if AC equals AB plus BC, there you are, then AB plus AB equals AB plus BC. This is called the substitution property of equality. Now I'll just say substitution property, and leave it at that because space. Now, how did I do that? I replaced AC with AB plus BC. So technically, or I could just write it out. I mean, either way, I wrote it out. You could also use the transitive property, but I already said substitution. We're leaving it at that. Now I have AB, and let me clean this up so I can see it because I'm at my last step and I need to see how I can get from 3 to 4. AB plus AB equals AB plus BC. All of a sudden, it's now AB equals BC. Well, how can I go from 2 things on the left and 2 things on the right to 1 thing on the left and 1 thing on the right? I would have to get rid of 1 from each side. There's an AB on the left. There's an AB on the right. If I subtracted AB from both sides, that would cross out and give me AB equals BC, which is that guy right there. So what did I do to both sides? I subtracted. So what is this? The subtraction property of equality. I can squeeze it in. Depends on what kind of teacher you have. They might be okay with you saying subtraction property. I like to write out as much as I can because it sounds a whole lot better. But this is an introduction to a 2-column proof. And with 2-column proofs, again, you're given information, you're told to prove something, and you have to go from step A to step whatever and explain what you did. And oftentimes with segments, we're going to have to do segment addition postulate. Oftentimes substitutions involved. And in this case, we had subtraction too. So lots of fun. I enjoyed it. Thanks for watching. More to come. All right, kids, what do we have here? We have a 2-column proof and a whole lot of blanks to fill in, a whole lot of them. In a previous video, I gave you all the statements and I had to give you all the reasons. Well, now we're everywhere. And what I have here is a bunch of angles glued together. I have a straight line here. I got what looks like it could be a right angle, but I don't know. I got these angles are next to each other. Anything could happen. But what it's telling me to right off the bat is angle AEB, which is 1, 2, 3, is complementary to angle BEC. So angle AEB is complementary to BEC. Let's get started. And what I have to show is I have to show that the measure of angle AED, which is U, is 90 degrees. So got a lot of work to do. Step number 1 is always your given. So there you have it. Step number 1, AEB is a complement of BEC. That was my given. My reason is given. 90% of the time, 99% of the time, your first step in a 2-column proof is going to be your given. So let's not burn too much brain energy on that. Step 2, statement 2 is, I don't know. But it says the reason is definition of complementary angles. What does complementary angles mean? 2 angles that add up together. Oh, so what they might want us to say is by definition of complementary angles, the measure of angle AEB plus the measure of angle BEC is going to be 90 degrees. All right, I can handle that. Measure of angle AEC is equal to the measure of angle AEB plus measure of angle BEC. Okay, well, what's AEC? All right, this whole thing right there. And that's the measure of angle AEB plus the measure of angle BEC. Oh, I see. They want me to show that this whole thing is that guy plus that guy. Well, whenever we add two angles together, the reason why we're allowed to add those angles together is because of the angle addition postulate. In a previous video, you saw me do segment addition postulate, and then I said later we're going to do angle addition postulate. Well, here we are later. I hope you're watching all the videos, otherwise none of this made sense. But angle addition postulate is a rule that says, hey, you're allowed to say that one whole angle is equal to two angles added together. The measure of angle AEC is 90 degrees. Now, that's because the measure of angle AEC is 90 degrees. Now, usually when we get to a part where we look up here and we don't see a whole lot, we're trying to piece two previous pieces of information together. I see a 90 degrees up here. I don't see any 90 degrees in my given. I don't see any 90 degrees on my picture, and you're not allowed to go from your proof. So I have to look at previous information, and I see that 90 degrees lives up here in step 2. Let me give you a circle. Also, the measure of angle AEC is right here. Oh, AEB, BEC, AEB, BEC. I know the measure of angle AEB plus the measure of angle BEC is 90 degrees because if I were to say that guy equals 90 and that guy also equals AEC, then AEC equals 90. This is the substitution property. And if you're like, whoa, 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 what just happened? Let me explain it again. Let me explain it again. If I gave you a problem that was like A equals B and B equals C, I'm allowed to say A equals C. Because if A is B and B is C, well then B, these guys are the same thing too. So 90 equals A, B, B, E, C. AEC equals A, B, B, E, C. So since AEC equals 90, that's because we just replaced that guy and that guy with each other. Okay, substitution property. Now we're down to the measure of angle AED plus the measure of angle AEC equals 180 degrees by the definition of supplementary angles. So even though I don't say supplementary up here, I see that all of this gives me a perfectly straight line. So they're saying, well, let's just add AED, which is U, and AEC, which is U, and make it 180. My next step is to do the substitution property of equality. So what they want me to do is they want me to replace something up here so that I can go from 5 to 7. Now, if I just said something about AEC equaling 90 degrees and I see AEC appear and I kind of don't want it to be there anymore because it's now gone in 7, why don't I just replace AEC with 90? The measure of angle AED plus 90 equals 180 degrees. Now, that is substitution because I substituted 90 for AEC. My last step is to go from AED plus 90 equals 180 to just get rid of that 90 and make it 90 over here. How do I do that? Well, if I subtract 90 from both sides, then AED equals 90. If I just subtract 90 from both sides. So what am I going to do? The subtraction property of equality. Subtraction. Ugh, looks terrible. Property of equality. And so there's my proof. Okay, this is still like an introduction to two-column proof. So again, you're going to see me filling a whole lot of blanks, but this used a lot of angles and a lot of reasons. But a lot of angle addition problems and a lot of segment addition proofs are going to involve you like adding stuff, substituting information, and probably doing some kind of solving an equation type thing, which is exactly what we did here. It's just this one was a lot more involved than my previous video if you watch that. But we're on our way. Not easy stuff. That's why this is called gross geometry, because it's not that much fun. Unless you're sick, in which case gross geometry should be right up your alley. Given the measure of angle 1 equals the measure of angle 3, I need to prove that EBA, which is this chunk right here, is equal to the measure of angle CBD. That chunk right there. All right. I got myself a two-column proof. All of my reasons are given. Some of my statements are given. I need to go from 1 to 6. Well, if you are watching my videos in order, if you're watching my gross geometry videos in order, which if you're not, shame on you, the two previous examples looked very similar to this, where my first statement was always a given. It even tells me it's a given, so why would that change? 95, 91, 90, 10, 90 billion% of the time, your first statement's going to be your given for a two-column proof. So that's done. Now what? They are going to tell me that the measure of angle EBA, which is this whole thing right here, EBA is 2 plus 3, angle addition postulate, makes sense. We saw that in a previous video. The measure of angle EBA is also 2 plus 1. How do I know that? Well, 3 is 1 because we said that up here. So if 3 is 1, then my reason from turning 3 into 1 is because 3 is 1. That's the substitution property of equality. So we've seen that before. They could have made this problem a little bit more difficult and made me guess that, but I'm not going to complain. So now it says the measure of angle EBA equals blank from the commutative property of addition. Now, the commutative property of addition means that if you say something like 3 plus 1, it's the same as 1 plus 3. You're going to look at this and say, this is extremely picky. I don't like it. And you're kind of right. But the difference between 3 and 4 is 3 says 2 plus 1. 4 is going to be 1 plus 2. Pointless? Yes. But many proofs are. Proofs are annoying, but commutative property, if it says, no, you need to use the commutative property, just think of a commute to work. If you take route 3 to work and then take route 1, then on the way home, you're going to take route 1 to route 3. Makes sense? It should. So now the measure of angle 1 plus the measure of angle 2 equals stuff from the angle addition postulate. So let's go back to our picture, because the last time we used the angle addition postulate, we said that 2 plus 3 is EBA. Now I want 1 plus 2, and 1 plus 2 is CBD. So we are going to say that the measure of angle 1 plus the measure of angle 2 is the measure of angle CBD due to the angle addition postulate. And so now I'm at the very end. And what always happens at the very end? What you're trying to prove. So we could say the measure of angle EBA is congruent to that, is equal to the measure of angle CBD by the transitive property of equality. The transitive property of equality is kind of like the law of syllogism. The law of syllogism says, hey, if A equals B and B is C, then just skip the B and go right from A to C, A to C. Transitive property is the same thing. So what are they doing here? Way up here, they say that EBA is 1 plus 2. 1 plus 2 is CBD, so let's skip the middleman and say EBA is CBD, and that was supposed to be EBA, so let me erase that and make that look better. Otherwise, that would not be a good way to end this video, to have a wrong statement up on the picture. But despite that tiny little mistake, That's my guy. So that's my introduction to column proofs. Not a lot of fun unless you have a death wish. So there you go. Make a flow proof. What's a flow proof? Is it like a flow chart, you ask? Kind of. Flow chart is like, if I do this, then that happens. And if I do that, then this 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 happens. That's a flow chart. A flow proof is kind of like the same thing, but with statements and reasons instead. So I'm going to prove this by making a flow proof. What do I got? I am being told that segment AD is congruent to segment CE. So AD is U, congruent to segment CE, that's U, okay. And I need to prove that AC, which is U, is equal to DE, which is U. So segments that are made up of one or two more segments. Probably we're going to deal with segment addition, postulate, stuff like that, but I don't want to, take away from the excitement of finding out what's going to happen. Let's just get started. Segment AD is congruent to segment CE because that's the given. You always start out with the given. Now I'm going to put the given in a box. It all depends on what your teacher or professor or whomever, the book that you're using, wants you to do as far as flow proof stuff. But I like to put my reasons in the box. What's in the box? The reasons. 7. Also Incubus, I think. No, Hoobastank is the reason they wrote that song. Very popular about 25 years ago when I was young. All right. It looks like to me that I'm starting out with segment congruent to a segment, distance equal to a distance. They probably want us to make things look like that. So what I'll do is I'll switch this up and make it AD is equal to CE and blame that on the definition of congruent. I said define. Oh, off to a banging start. Definition of congruent or congruence. But that's what I'm going to do. It's proper to do as many steps as you can, even if it looks sloppy. And in this, it might look a little on the sloppy side, but you know what? There's only like 5 of you guys watching this anyway. Now what? Well, I need to go from AD and CD to AC and DE. So how can I do that? How can I turn these guys into these guys? Well, AD includes AC because AD is AC plus CD. So let's say that. Let's say that AD is equal to AC plus CD. Now, when you take two segments and add them to make one more segment, that's called the segment addition postulate. I have a feeling that's going to happen again almost immediately. Postulate. All right, segment addition postulate. All right, so if I do that with AD, I mean, it makes sense that I should do the same thing with CE. So let's take this arrow, bring it up here. Look at me flowing. I'm going to say the same thing with CE, that CE is the same thing as CD plus DE. And that too is the segment addition postulate. The SAP, as people from Canada would say, because they like maple syrup. This is what I get for talking and punning at the same time. Postulate. All right. No more. I'm done. I'm done entertaining until I get this complete. All right, so now that I said what CE is, and now that I said what AC is, I notice that I have CD and I have AC, and I should be able to isolate them, right? My job is to get AC and DE all by itself. So why don't I get AC all by itself by subtracting CD? And why don't I get DE all by itself by subtracting CE? And I'll do that all in one big step. So what I will do is I will take this one, I will subtract CD from both sides to get AC all by itself. So AC, if I subtract CD, AC is going to equal AD minus CD. Similarly over here, if I get DE all by itself, it's because I subtract CD from both sides. So DE equals CE minus CD. All right. So now I have oh, and by the way, I did that because I subtracted stuff. So that is the subtraction property of equality. Subtraction property of equality. Let's put it in a box and draw an arrow up to here. Flowing once again, like a rapper. All right. So I need to get AC equal to DE. AC is AD minus CD. AC is CE minus CD. Oh, that's a shame. If only these guys were the same, then I could say that these were the same. Oh, wait a minute. AD and CE are the same. So if I take one of these, if I take DE, for example, and I replace CE with AD, I now have AD minus CD. And what I did is I rewrote DE equals and replaced CE with AD. So I used the substitution property. Running out of room, so I'll put prop. Okay. Now my last step is now that I know that DE is AD minus CD, and AC is also AD minus CD, that means that AC and DE are the same. AC equals DE. And I could use the transitive property. I could use the substitution property. I haven't used the transitive property yet today. By the way, the transitive property says that if A equals B and C equals B, then A equals C. That's the transitive property. So that works here. Transitive property of equality. I am done my flow proof. So I'm going to be honest, flow proofs aren't used a whole lot in geometry. They exist. They are done. You know, if you're taking a high school geometry course, you'll have a teacher do 1, 2, or 3 of them. Maybe have you do 1, 2, or 3 for homework. Maybe have you do 1 for a quiz, 1 for a test. But then they kind of disappear. If you're watching my videos one after another, you are usually going to run into 2-column proofs a whole lot more. But flow proofs are still out there. They still exist. And in a way, I did this the same exact way I would do a 2-column proof. These are my statements not in the box, and my reasons are in the box. It's just a different way that it looks. And in my opinion, it's uglier. But I'm not here to judge beauty. That's up to judges of beauty pageants. Like and subscribe. Make a paragraph proof. A paragraph proof is basically like a flow proof with more words, more sentences. If you remember from a previous video, those of you who watch all my videos in order, the flow proof looked like this, right? Where we said, the statement is blah, 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 and the reason is this. And the statement is blah, 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 and the reason is this. Well, now, instead of having a picture of a flow proof, it's going to be just in flat out sentences, and we're going to make it sound like a little essay. Okay. All right, so what do we have? We have given KMN, so KMN is 28 degrees. I can handle that. We're also given the fact that PTS is 118. I have to prove that JMK, the angle, this guy right here, is congruent to angle STR, which is this angle right here. Okay, so I have to show that these guys are congruent by using numbers like 28 and 118. Let's start out with the given like we always do. We are given, now keep in mind, little warning, just because I write it out this way doesn't mean it's the only way of doing it. Those of you who watch my videos know that I stumble and fumble over my words all the time. I accidentally misspeak. I misspell words all the time. Don't be like, wow, that guy is the Lord of grammar. No, trust me, no. It's just the way that I'm doing is a way that's correct, but certainly not the only way. So we are given that the measure of angle KMN is 28 degrees and the measure of angle PTS is 118 degrees. Period. End of sentence. All right, how can I start connecting these dots? I need to find a way to connect green with purple here. So why don't I find out what green is? Why don't I find out what purple is? And I'm sure at some point I will find out that they're the same. Now, what I know is I see that right angle right there. Okay, that right angle right there. So what I can say is that angle JMK and angle KMN add up to 90 degrees by the definition of right. No, let's not say right. Let's say complementary angles, because right angles implies one angle. So let's say by definition of complementary angles. Complementary angles is just more proper. Complementary angles. So maybe what I should have said is that the measure of angle JMK plus the measure of angle KMN equals 90. Probably a better way to say it. Already my paragraph proof isn't falling apart. It's just much worse than it has to be. Now, if that's the case, what I can do is I can replace measure of KMN with 28. Using substitution, the measure of angle JMK plus 28 equals 90. Now, I can solve for JMK by subtracting 28. So, the measure of angle JMK equals, what is that, 62 using the substitution property. Nope, the subtraction property. Subtraction property. Cool, so what I have that you are now 62. Now, a lot of this, most of you kids watching this would be like, dummy, I know that I could just do 90 minus 28 and you wrote out like half a paragraph just to say that. Do we really have to do these for proofs? Yup. That's why this series is called gross geometry. It's not called easy happy time geometry. Easy happy time geometry is for you Khan Academy jerks. I apologize to the Khan Academy jerks. If they want to sponsor any of my videos, I'd be very happy. Now, I found out what the measure of angle JMK is. Why don't I say that the measure of... Now, what I'm going to do is I'm going to avoid writing so much here and just kind of jump right to that and say that the measure of angle STP, Stone Temple Pilots, plus the measure of angle PTS equals 180 by definition of supplementary angles. See, these guys add up to make 180. And I'm hoping by doing 180 minus 118, I get 62. I do. And if I get 62, then I can show that these guys are the same. So what I can do now, since I can't ever make it that simple because proofs are a nightmare, what I can do now is I can go back up here and remember that PTS is 118. So the measure of angle, was it supposed to be STP? Wait, that's an R? Oh my gosh. R. So that Stone Temple Pilots joke is dead. And that's still PTS. STR, PTS. All right, I'm good. I just, I don't have my glasses on, so I really can't see anyway. The measure of angle STR, okay, plus, let's change PTS, is 118 equals 180 using substitution. If I subtract 118 from both sides, I get that the measure of angle STR equals 62 using the subtraction property of equality. Now that I know that the measure of angle STR is 62, and I found out up here that the measure of angle JMK is 62, I can now finally say that JMK is the same as STR. But first, I have to say the measure of JMK is the same as the measure of angle STR using the transitive property. Transitive property says if A is C and B is C, then A is B. So that's what transitive property is. So using the transitive property, and now, if their measures are the same, we can finally end this thing and say angle JMK is congruent to angle STR by definition of congruence. I nailed the spacing. Very proud of that. But this is a paragraph proof. Okay? This is a paragraph proof. Normal people, including myself, before you start your proofs, what you really should do is you should be like, well, if my job is to prove that this guy is the same as this guy, I know that that's a right angle, so 90 minus 28 is 62. And this is 180 degrees, so 180 minus 118 is 62, so these are the same. And this is what you have to do to prove it. It's the proof that's a nightmare. And it is a nightmare. But the best thing about nightmares is eventually you wake up. I think that's in the Bible. Or if I just made it up, I don't know. Like and subscribe. Make a paragraph proof given B is the midpoint of AC, C is the midpoint of BD, prove that AB equals CD. All right, so what's a paragraph proof? It's a proof where, you say given blah, 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 then blah, blah, blah because of this property, then blah, blah, blah because of that property, then blah, blah, blah because of that property, and therefore AB equals CD. So what do I have to do with this problem? Well, I have to state the given first, and the given is B is the midpoint of AC. So here's AC, B is the midpoint, which means that's going to happen. Okay, what else do we know? We know that C is the midpoint of BD, so C is the midpoint of BD, which means that is going to happen because by definition of midpoint. And so by using this, I need to show that AB is congruent to CD. So probably a lot of segment addition postulate stuff, probably a lot of this guy's congruent to that guy, this guy's congruent to that guy's stuff. And we have to put it in a paragraph using sentences and stuff like that. So we are given your first statement, your first sentence, your first step is always the given. We are given B is the midpoint of AC and C is the midpoint of BD, period. So I said this in a previous paragraph proof video, don't cling on to my wording structure because I'm terrible at writing sentences. I'm just doing it so that it's right. I might have misspelled words. I might have to erase. I just know it's right. Now, what I also know what midpoint means. Midpoint means takes a line segment and cuts it in equal parts. So we could say by definition of midpoint, we could say that AB equals BC. And while we're at it, let's take care of this one too. And BC is congruent or equal rather to CD. Now you're going to love this because this problem or this proof is done after this sentence. If AB is BC and BC is CD, then by the transitive property, AB is CD. So let's say that by the transitive property, AB is CD. And that's it. We're done. So I was expecting this problem to be a whole lot worse than it really was, and it really wasn't that bad at all. Sometimes paragraph proofs aren't that bad. In a previous video, it was bad. In this one, it was not. But yeah, here's paragraph proofs for you. Tons of fun. Write an indirect proof to show that the square root of 18 is not 3 root 6. What the crap is an indirect proof, you ask? Well, let's first assume the opposite of the conclusion here. Conclusion. I don't even know if that's spelled right. What's the conclusion? That's the conclusion. The second part of what you're trying to prove. Let's assume the opposite. In other words, to do this problem, we're going to assume that the square root of 18 is 3 root 6. Then what we do is we do some work, whatever work we have to do, and arrive at a contradiction? What's a contradiction, you ask? It's a lie. Basically, your girlfriend is all like, you talking to girls, and you all like, no, I'm not. And then she like, let me see your snap. And you're like, oh, all right. And then you hand over your phone and she like, I'm going to assume that you're telling the truth, but I'm going to check your phone anyway. And she look at your phone and she slides into your DMs and she sees that all these other girls are sliding into your DMs. So her assumption that you were telling the truth is wrong. Therefore, you are lying and therefore you are talking to girls and looks like you're finding yourself a new girlfriend. What we're doing is we're going to assume the opposite. Find out that the opposite is wrong and say, well, that's wrong, so therefore the original statement that we are given was true. Okay? So one more time, we're going to assume the opposite of this. We're going to do some math and find out that that's not right, which means if the math doesn't work out, they can't be equal. Therefore, this can't equal that. So let's try it. Let's give it a shot. Let's give it a shot. Let's give it the old college try. Okay. Now, as with all of my proofs and paragraph proofs, just because it's the way I write it doesn't mean it's the only way. It's just a way that is correct. All right. So let's assume that the square root of 18 is 3 times the square root of 6. Well, I know from a math teacher named Mick Parrish, the math teacher that the square root of 18 can be broken down to the square root of 2 times 3 times 3. And you can rip out a group of 3s, and you are left with 3 times the square root of 2. Wait a minute. Root 18 is supposed to be 3 root 6. We just found out that root 18 is actually, and let me write it out so it looks a little bit better, root 18 is actually 3 root 2. Okay, so I'll say that. But we assumed this, but root 18 is actually 3 root 2. Therefore, root 18 can't be 3 root 6. So we'll say that. Root 18 cannot be equal to 3 root 6. And we're done. That's our indirect proof. We assume that the opposite of that occurs. We find out that our assumption is wrong. Therefore, since our assumption is wrong, the original assumption must be right. Indirect proof. All about you cheating on your girlfriend or boyfriend. Make an indirect proof. If the measure of angle A, that guy, and the measure of angle, is 64, and the measure of angle B, that guy, is 116, then A and B are supplementary. What's an indirect proof? I already made a video on indirect proof, so I'm not going to break it down. But first things first, we are going to take the second part of what we're trying to prove and assume the opposite. We're going to assume that they're not supplementary. Then we do some math, find out that we're wrong, and therefore they must be supplementary. Okay, so that's indirect proofs in a nutshell. You assume the second part is a lie, do some math, and find out, whoopsies, I was actually wrong by assuming that, therefore the original must be true. So let's assume that angle A and angle B are not supplementary. Supplementary means they add up to 180 degrees. Supplementary means they add up to 180 degrees. Let's get a different color. The measure of angle A is, I'll say the measure of angle A plus the measure of angle B is the same thing as 64 plus 116, which is 118. So we're assuming that the measure of angle NB are not supplementary, but when I add angle NB, A and B, but the measure of angle A plus the measure of angle B add up to 180, which means they are supplementary. And I can end it right there. I mean, I'll need to make an extra sentence to make it sound prettier. I know in my previous indirect proof video, I made it an extra sentence. But again, clinging onto the way that I structure this is not necessary. All you have to do for an indirect proof is assume the opposite of the other part, the second part, find out that you're wrong, which means the original thought, the original statement is actually correct. And that's what we did here. Indirect proofs, tons of fun. All about lying. Given points A, 2 and 3, and B, -2, 5, make an indirect proof to show that C, 0, 3 is not the midpoint of AB. All right, so with an indirect proof, what you have to do is assume the opposite of the second part that you're trying to prove. So it says, make an indirect proof to show that C, 0, 3 is not the midpoint. Let's assume that C is the midpoint of AB. So let's do that. Let's find out what the midpoint is. Let's break out the midpoint formula. M equals x sub 1 plus x sub 2 all over 2, comma, y sub 1 plus y sub 2 all over 2, and point. If I call you x sub 1, y sub 1, call you x sub 2, y sub 2, then the midpoint is going to be 2 plus -2, x sub 1, x sub 2, all over 2, comma, 3 plus 5 all over 2. 2 plus -2 is 0, 0 over 2 is 0. Okay? 3 plus 5 is 8, 8 over 2 is 4. So we assumed that C, 0, 3 is the midpoint. We found out that the midpoint is actually, and I'll say that, the midpoint is actually 0, 4. So we can end up by saying, so C, which was 0, 3, is not the midpoint. All right, so I kind of like indirect proofs. This one was actually pretty fun, pretty easy. I enjoyed this stuff, the point of the midpoint. And I'm sure a lot of you Gen Zers are like, the point is mid because of slang. Anyway, the whole point of doing indirect proofs is I give you a statement, you assume the second part's wrong, you do some work and realize, oh, whoops, maybe it was right, and then state that it was right. So you admit defeat. So all about lying and having to fess up for your own mistakes. Indirect proofs, just making me more depressed as time goes on. Reminds me of my marriage. Like and subscribe. All right, we are given a 2-column proof where we are also told that A and B are parallel lines and C and D are parallel lines. And from this, we have to show the measure of angle 2 plus the measure of angle 11 is 180. Whenever you're dealing with two-column proofs, you take what you're given, allow that to formulate some kind of game plan in your mind, and probably make yourself a rough draft before you actually get started. So you take what you have and you kind of allow yourself to go from point A to point B. Okay, and find a way to connect these two. Now, if I look at 2 and 11, they're not connected. I need to find a way to connect 2 and 11. So I'm going to make myself a little game plan here. And step number 1 is going to be given. Always given. I'm not touching this yet. I'm not there. So let's try to get from 2 to 11 somehow. So I can take the fact that 2 and 10, for example, 2 and 10 are congruent because they correspond. Since C and D are parallel, 2 and 10 are equal because they correspond. Can I get from 10 to 11? Not really, but what I can do is I can go from 10 to 11. I can say that since C and B are parallel, I can say that 10 plus 11 is 180. And that's because the interior same side angles add up to 180. So since 2 is 10, I can finish this out in one more step by saying, since 2 is 10, why don't we replace that 10 with 2 and say 2 plus 11 equals 180, and that is by substitution. I'm done. All right, so I am going to now complete this two-column proof with this information and make it look a lot prettier. And, of course, using all the appropriate symbols, because in my rough draft, in my mind, I don't really care about the symbols as long as I know what I'm doing. So A is parallel to B, C is parallel to D, and the reason for that is because it's given. Always, always, always start out with your given statement. What was 2? 2 was 2 is equal to 11, 10, I mean. So we're going to say that the measure of angle 2 is equal to the measure of angle 10. And once again, that's because 2 and 10 were corresponding angles and C and D were parallel. So we could say the definition of corresponding angles. Use symbols. You're allowed to. What color did I use next? Green. 3. We said in 3 that 10 and 11 are the same. No, they're not. 10 plus 11 is 180. The measure of angle 10 plus the measure of angle 11 is 180 degrees, and that's because interior same side angles are supplementary. Last but not least, now that I know that 2 is 10, I can replace that 10 with 2 and say the measure of angle 2 plus the measure of angle 11 equals 180 degrees, and that's using the substitution property. So when given a bunch of parallel lines, use that. You're going to use words like interior angles or alternate interior angles, alternate exterior angles, corresponding, same side, supplementary. You're going to use all of that to your advantage. And from there, we were only able to do this in 4 steps. So not so bad. I'll take it. Given angle 1 and angle 4 are supplementary, we need to prove that A and B are parallel. Now, there's a bunch of ways that you can prove that A and B are parallel, and here they are. You can show that two lines are parallel if corresponding angles are congruent, if alternate interior angles are congruent, if consecutive or same side interior angles are supplementary, means they add up to 180, if two lines are parallel to the same line, if two lines are perpendicular to the same line, or if alternate exterior angles are congruent. So those are the ways that we can prove that A and B are congruent. Let's see what I'm going to do. Whenever I have a two-column proof, I like to make a little bit of a rough draft. So I need to get from 1 to 4. Actually, I have 1 and 4. They're supplementary. So I need to show that A and B are congruent. So maybe I could take 1 and 4 and use that to connect 3 to 2. And once I show that 1 and 2 are congruent, then I have corresponding angles are congruent, therefore A and B are parallel. So that's my goal. Take 1 and 4, get to 2, and show that 1 and 2 are congruent. So a little rough draft over here. 1 plus 4 is 180. From that, I can say that, well, since what am I told? I'm told that C and D are parallel. That means 3 plus 4 is also 180, right? Now, I can look at this and say, like, okay, well, I see 4 in common, but that doesn't really do much for me. I also see that since they're both equal 180, I could say 1 plus 4 equals 3 plus 4, but that doesn't really help me. Not yet. Because if I were to do that, that gives me 1 equals 3. I'm not there yet. And I want to connect 1 and 2. I need to get 2 involved. But you know what? 3 and 2 are the same thing. 3 is 2. So I can now say that 2 plus 4 is 180. So if 1 plus 4 is 180 and 2 plus 4 is 180, then 1 plus 4 equals 2 plus 4. There's a 4 on the left. There's a 4 on the right. They cross each other out. 1 equals 2 gives me exactly what I want to make this proof happen. So that's the order that I'm going to do things. I'm going to start first off with my given. Okay? Angle 1 and angle 4 are supplementary. Abbreviate, you're allowed to. Also, C is parallel to D, and that's going to be my given. Always, 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 always start out with your given. Now, if 1 and 4 are supplementary, that allows me to say that the measure of angle 1 plus the measure of angle 4 equals 180 degrees. Now, I didn't write all the cute little symbols over here because this is my rough draft. I just have to make sure that I write my symbols over here. Now, the reason for that is the definition of supplementary angles. Look, abbreviations again. Use them. Do it. Do it. All right, what else did I say? I then said that the measure of angle 3 and 4 add up to 180 degrees. And that is the definition of same side interior angles. Once again, being a little bit lazy with my wording because I don't have a whole lot of space to deal with. If your teacher lets you be lazy, be lazy. If they don't, don't. But again, I'm being lazy here because space is limited for me. I'm not the best drawer. Good thing I'm not a dresser, am I right? 4. 4, I was able to say that the measure of angle 2 is equal to the measure of angle 3, and that's the definition of vertical angles. Don't know why I didn't just do those quote thingies again. Too late. Too late. Where am I now? I now know that since 2 and 3 are the same, I can rewrite line 3 and make this the measure of angle 2 plus the measure of angle 4 equals 180. And that was using substitution. So substitution, property of equality. So I'll just say substitution prop. Okay. Going back to red. Since 2 plus 4 equals 180 and 1 plus 4 equals 180, then the measure of angle 1 plus the measure of angle 4 equals the measure of angle 2 plus the measure of angle 4. And I could use substitution. I can use transitive property. I like transitive property, so let's use transitive property of equality. Last but not least, I could subtract the measure of angle 4 from both sides. I could subtract the measure of angle 4 from both sides, and that tells me that angle 1 is equal to the measure of angle 2, and that's the substitution property of equality. Subtraction property of equality. All this got me to that point where now 2 equals 1, 2 and 1 correspond, 2 and 1 are equal, which means A and B are parallel. So last but not least, I can't use green because it'll blend with the green down there. So let's go back to black. I could say that A is parallel to B, and that's because corresponding angles are congruent. Corresponding angles are congruent. All right, so this falls under the category of proving lines are parallel. Usually you have geometry books with sections dedicated to proving lines parallel. And when you're trying to prove lines parallel, you look at the 6 options that I gave you at the beginning of this problem and try to make one of those things happen. I did by showing that 1 and 2 are congruent, therefore A and B are parallel. And I'm done. All right, we got a 2-column proof. We are given angle 1 and angle 2 are congruent. We're also given P and Q are parallel. I need to show that Q is perpendicular to A. So in order to show that Q is perpendicular to A, I need to show that 1 and 2 are 90 degrees. So this is actually not too bad. All right, I have my given. What I always like to do is I like to make myself a rough draft over here. So if I'm given the fact that 1 and 2 are congruent, and also 1 and 2 are directly next to each other and form a straight angle, 1 plus 2 is 180. I'm also told that 1 and 2 are the same. So I could say 1 plus 1 equals 180, and that's the substitution property. If I combine like terms, 2 times angle 1, I know this doesn't look right, but this is a rough draft and I know what I'm doing. So 2 times angle 1 is 180. Divide both sides by 2, and angle 1 equals 90. Which means angle 2 is 90. Which means since 1 and 2 are 90, in fact, I don't even need to say the fact that 2 is 90. I could skip that part. Once I know that 1 is 90, I have enough information to finish my proof and say Q is perpendicular to A. So let's set this up using all this information over here. All right, step number 1 is always going to be your given. Angle 1 is congruent to angle 2. and P is parallel to Q. I rhymed. Always appreciate that when I can make a song out of my proofs. Speaking of which, Proof is the name of a dead rapper, so he did a lot of songs. The measure of angle 1 plus the measure of angle 2 is 180 degrees. We said that because they're right next to each other. So we can say the definition of supplementary angles. Definition of supplementary angles. Look at me being lazy and abbreviating. You're allowed to do that if your teacher lets you. What did I do next? Well, since I know that 1 and 2 are the same, I said the measure of angle 1 plus the measure of angle 1 is 180. So I replace 2 with 1, and whenever you replace something with something else, that's the substitution property. Substitution prop. 4 is, since the measure of angle 1 is right next to the measure of angle 1, why don't I just say I have 2 of those measure of angle 1s and set that equal to 180. What do we do there? We combine like terms. If I divide both sides by 2, I got the measure of angle 1 is 90 degrees. So I divided both sides by 2. That's the division property of equality. So I'll say division prop. Now that I know that the measure of angle 1 is a right angle, I have enough information to prove that Q is perpendicular to A. And that's by the definition of perpendicular angles. So I like it. I'm happy with it. I'm sticking with it. I'm trying to think if there's anything I need to add to this video, and I really don't. It's pretty straightforward. It's just you have to make your rough draft and then go from there. And, it's a pretty clean proof. I'm happy with it. Holy bonfire on my Aunt Sally's lawn. Look at the size of this thing. This is going to be a nightmare. Look at all the information we're given. Look at all this stuff. Look at what I'm trying to prove. It's everywhere. So what I need to do is I need to go from all of this info and show that BAE, which is U, is congruent to BCE, which is U. So I'm told stuff about parallel lines, so I'm probably going to have to deal with alternate interior angles, or maybe some type of angle, but it looks to me more like alternate interior angles. I'm told that BE, this uppy-downy thing, and DF, this lefty-righty thing, are perpendicular. That gives me the 90-degree angle. I'm also told that AEB and CEB are the same. So I have a lot of stuff going on here, and the first thing I'm going to do is make myself a rough draft. So I'm not even going to try to do this right away. I'm going to save the parallel line stuff. I'm told that BE is perpendicular to DF. So what that means, if BE is perpendicular to DF, I can start out by saying that the measure, and again, this is a rough draft that I'm about to make, so don't cling to the fact that I'm not using the proper symbols and stuff like that. I could say that BED and BEF are both 90. BED is 90 bed, and BEF is also 90. I know that BED is BEA. Actually, they want me to do AEB. I hate it when they put it out of order. BED is these two guys added together. So AEB plus AED, a shocking angle, If you get it, you get it. Is 90. Also, BEF consists of BEC, but they want me to write it out as CEB. So CEB plus CEF is 90. Angle addition postulate. What do I know? I know that these guys are the same. So why don't I just take one of them and replace one of them with, like, I don't know, why don't I take this AEB and replace it with CEB? So I have CEB plus AED equals 90. You don't change. You don't change. You don't change. So since they're both 90, why don't I try this out? Why don't I try the transitive property and write out CEB plus AED, which equals 90. Since that equals 90, they're now equal to each other. So CEB plus CEF. Now, what I can do is, since CEB is on the left and the right, I can subtract that out and end up with AED equals CEF. Now, this is terrific news because AED is this guy right here. AED is this guy right here, which is congruent to A or BAE. Okay, they want me to use BAE, not CAE. Annoying, but that's what they want me to do. These guys are congruent. Why? Because this is parallel and these are alternate interior angles. So I can say BAE is congruent to AED. And I can say that CEF, which is this guy, is congruent to C. How do they want me to write it out? BCE. BCE. And that's because of the parallel line stuff. So since AED is CEF, I can write out BAE instead of AED is equal to, and instead of CEF, I can write out BCE, and that's what I want to do. So there's a lot going on here. This is my rough draft. We're going to have to write small, so here I go, my given. Oh my gosh. Time is money, space is money. This is my given. Given. Okay, don't leave comments like, you're lazy, I hate you. Only 3 people watch these movies anyway. And if someone actually does watch this and gets this far, please do write in the comments, why you're lazy, I hate you. I would appreciate that. All right, the measure of angle BED, now I have to bring back my symbols to be appropriate. The measure of angle BED is 90 degrees. And the measure of angle BEF is 90 degrees. I'm going to regret putting that in 2 lines. I'm going to run out of room. The reason for that is the definition of perpendicular angles. Okay? Let's get smaller. Aim small, miss small. Patriot. The measure of angle AEB plus the measure of angle AED is 90 degrees. And the measure of angle CED plus the measure of angle CEF is 90 degrees. That was because I added these two angles to get that. I added these two angles to get that angle addition postulate. I then said that CEB plus AED is 90 degrees, and I used substitution for that. So the measure of angle CEB plus the measure of angle AED is 90. And I use the substitution property for that one. Once I have this guy equals 90, that guy equals 90, I set them equal to each other. So that was the measure of angle CEB plus the measure of angle CEF equals the measure of angle CEB plus AED. Gosh darn it. That was transitive property. CB on the left and CB on the right cancel out, and that's because of the subtraction property. So that left me with AED is congruent or equal to the measure of angle CEF. And I did subtraction property of equality. I think I'm going to make it. That led me to go back to the parallel lines information and allowed me to say alternate interior angle stuff. So that was the measure of angle BAE was equal to the measure of angle AED, and the measure of angle CEF is congruent to the measure of angle BCE. And that was definition of alternate interior angles. And last but not least, since AED was BAE and CEF was BEC or BCE, then Bay is before Christ. Sounds like my dating history, right? The measure of angle BAE is the same as the measure of angle BCE, and that was substitution property of equality. Maybe you can get away with transitive for that one. Substitution. That was a nightmare. I don't know if there's a faster way that you could do it. I don't know if there's a way that you can do it in less steps, but you know what? You're not watching my videos to do it any better way. You're watching my videos because you love me. So, yeah, that is a proof where you need to use parallel lines and perpendicular lines to your advantage, and we did. Took a while. It was worth every second just to spend it with you. Like and subscribe. Given AB is congruent to CD, all right, you guys, and given BC is congruent to AD, so you guys prove that ABC is congruent to CDA. All right, when I'm being asked to prove two triangles are congruent, I'm having four major thoughts in mind. SSS, SAS, ASA, and AAS. And what I want to do is I want to try to find a way to come up with either one of these four to show that these guys are congruent. Well, looking at this picture, I have two sides already, which eliminates U2. Now, can I find a way to show that angles are congruent? No. I don't see a third side. Oh, except the fact that AC is like a common side with both of these triangles. So technically, right there. And I could use SSS. So this is a three-step proof, maybe. Proof, maybe. So let's get started. One is the given. All right, AB is congruent to CD, and BC is congruent to AD, given. Side, side. My third side is to show that AC is congruent to itself. So AC is congruent to AC. Now, whenever you say that a side is congruent to itself or an angle is congruent to itself, you are using the reflexive property. Now that I have all three of my sides, I can say that triangle ABC is congruent to triangle CDA. And the reasoning for that is SSS, side, side, side. Pretty quick proof, not so bad. Very intro to triangle congruence proofs. I like it. Given AB is parallel to CD and AB is congruent to CD, prove ABC is congruent to DCB. All right, I have two sides. That's all I'm given. So this is me doing a rough draft. Whenever I'm trying to do triangle congruency, I'm thinking four major proofs that I could use. SSS, SAS, ASA, or AAS. Now I have my sides. I have a pair of sides. Ooh, BC is congruent to itself. So I have a second pair of sides. So you're eliminated and you're eliminated. These parallel lines, what can I do with that? Oh, when I have two parallel lines, alternate interior angles are congruent. So I can say that I have a side, an in-between angle, and a side. I could use SAS for this. So I'm going to start out with my given, then I'm going to show that BC equals BC, and then I'm going to show that ABC is congruent to C or DCB, angles using the definition of alternate interior angles. So let's write out our given first. That AB is parallel to CD, and AB is congruent to CD, given. It doesn't matter the order that you do these. This is just the order that I discovered them. So I could say CB is congruent to CB, and whenever you say that a line is congruent to itself, that is the reflexive property. Okay, reflexive property. Now I could say that angle ABC is congruent to angle BCD, and that is by definition of alternate interior angles. Those parallel lines make this happen. Alternate interior angles. If your teacher lets you use shortcuts, take advantage of that. Now that I have a pair of sides, check, another pair of sides, check, and the angle in between, I'm allowed to say that triangle ABC is congruent to triangle DCB, and the reasoning for that is side, angle, side. So this required a little bit of thought, not too much, but yeah, not so bad. I'm done. Given OM is perpendicular to LN and OL is congruent to ON, prove that these two triangles are congruent. All right. So let's figure out what we have. We are given this that is a side. We are told that these guys are perpendicular, which means we are allowed to say that these two angles, and let me use a different color, let me use a different color, let me use a different color. We are allowed to say that these two angles are right, which means we could say that these two triangles are right triangles. Now I have, all right, so if they're right triangles, I have H, A, H, L, L, A, and L, L. So I have the ones involving a hypotenuse. So these guys are out of the question. So I have a hypotenuse. What else do I have? Oh, these guys are the same line. So if I can say that OM is congruent to OM, which I can, that gives me a hypotenuse and a leg. So I'm going to prove that these two are congruent. I could show that these two are congruent by HL. So let's go through all the steps. Step number one is the fact that OM is perpendicular to LN and OL is congruent to ON. That's my given. Always start out with the given. Step two is that angle OML is equal, or well, they are equal, but let's do the right angle stuff. OML and OMN both measure out to 90 degrees. So the measure of OML equals 90 degrees, and the measure of OMN is 90 degrees, and this is by definition of perpendicular lines. Okay? Which means we are allowed to say that the measure of angle OML is congruent to the measure of angle OMN, and that is through the transitive property. Now, a lot of people might be like, well, why do we have to write out both of those steps? You kind of do. It's dumb, but you kind of do. You have to show that they're 90 degrees, and then you have to show that they're equal. And now that they're equal, you're in good shape. Now, what I can say, let's use a different color, is OM is congruent to OM by the reflexive property. Whenever you say that two lines are exactly the same, because they are the same, you're using the reflexive prop. And since I showed that these guys are right triangles, I showed that I have a leg right there and a hypotenuse up here that was given to us. I can say that these two guys are congruent. OML is congruent to triangle OMN, and that's by using the hypotenuse leg postulate. My leg, SpongeBob. Remember that? Good times. Given WU is parallel to YV, XU is parallel to ZV, and WX is congruent to YZ, prove these two guys are congruent. All right, so these are my congruency rules. I have SSS, I have SAS, I have ASA, and I have AAS to the second there. I have congruent sides right there. Okay, so I have an S. Great. What it also gives me is I have two sets of parallel sides, two sets. Now, usually when it gives you parallel lines, you are thinking thoughts of alternate interior angles. Okay, alternate interior angles. These, but you know what? No, I don't want that here because that's not really what's going to help me. What I'm going to have is, since ZV and ZU are parallel, this acts as a transversal. These two correspond with each other. So these are going to correspond. Similarly, since these two guys are parallel, these correspond. And so what I have is I have an angle with the side in between an angle. I have ASA. So I'm going to state my given. I'm going to say that these two angles are congruent because they correspond. These green angles are congruent because they correspond. Therefore, the triangles are congruent from ASA. So, number one is my given. Okay, WU is parallel to YV. XU is parallel to ZV. And WX is congruent to YZ. That gives me my side right there, given. Okay, let's go with the red angles. Angle VZY is going to be congruent to angle UXW. And the reason for that is the definition of corresponding angles. Ready to kill two birds with one stone? Let's say that in the same exact statement. Why repeat myself? Let's say ZYV, angle ZYV, is congruent to angle XWU for the same exact reason. And if you're like, oh, yeah, you could do that in one step, why not? If you have the same exact reason, just give both statements in one. Don't overdo it. Now that I have an angle congruent, and the side that happens to be in between congruent, I can now say that triangle WXU is congruent to triangle YZV. And the proof that I used for that was ASA. That's it. That was actually friendlier than I thought. I thought it was going to be bad. But the only thing that's bad is Michael Jackson. You know it. It's a song. Look it up. It's called Bad. Rest in peace, Michael Jackson. Well, don't rest in peace, actually. Like and subscribe. Given angle XYW, which is XYW, that guy, weird, is congruent to that guy. I don't know why it just doesn't say that they're congruent. Why did it have to give me the right angles? But oh well, they're right angles. Also, we're told that this guy and this guy are congruent. This is weird. I need to show that these two lines, WX, is parallel to ZY. I need to show this. Now, I don't know this. I need to show this. So this is what I'm thinking. This is how my brain operates. There is a rule called CPCTC. Congruent parts and congruent triangles are congruent. Lots of congruence. It's corresponding parts of congruent triangles are congruent. Whatever. What that means is if I give you two triangles that are congruent, I can say that these guys are the same, and these guys are the same, and these guys are the same. So what I can do is if I show that these two triangles are congruent, then I can prove that these angles are congruent, which means I can show that blue plus purple is congruent to blue plus purple, which means by definition of alternate interior angles, I have parallel sides. I know that's a lot. Bear with me. Step number 1 is my given. Okay. Now my given, once again, gave me 2 angles. What I have is a shared side. That shared side is going to have to be explained. I have to say, and it's stupid, it's always been stupid, but WY is congruent to WY. And that's the reflexive property. My 5-year-old daughter is in the room and she's giving me a stink eye because I said stupid several times. It's a dirty word in this house, isn't it? She's nodding her head, I swear. Those of you who are addicted to my YouTube channel, that's the famous Kelsey. All right. Now I have 2 angles. Ooh, and a non-included side. That's AAS. So I can say that these 2 triangles, so let's put it in order. Y matches up with W. So let's make sure I say that. Y matches up with W. Z matches up with X. So X, Z, and what's left? Y, hold on, Y, Z, W, W, X, Y. And the reason for that is AAS. Now, that's maybe we're halfway done. Now, the purpose of me showing that these 2 sides or these 2 triangles are congruent is now I can say that these 2 angles are congruent. These 2 angles are congruent. So I can say the angle XWY is congruent to angle WYZ. And the reason for that is now that these are congruent triangles is that corresponding parts of congruent triangles are congruent. Okay? Okay. Step 5. This angle, ZWY, plus YWX equals angle, I did these 2, so XYW plus angle ZYW. Yep. And the reason for that is a bunch of substitution that I did up here without doing a whole bunch of substitution. So my reason for that is substitution property. Since these 2 guys are the same thing, right? These combine to make alternate interior angles. Maybe let's add one more step. Let's say ZWX is congruent to XYZ. And the reason for that is the angle addition postulate. 1 letter away from a retirement plan, AARP. And now that we know that, these 2 angles are all completely the same, these 2 guys are the same as these 2 guys. Now that we know that, I can say that this is parallel to that, thus finishing my proof. Let's get a different color. I can say that WX is parallel to ZY, and that's definition of alternate interior angles. So this problem wasn't pleasant at all. Not at all. Not one bit. I had fun though, and I said a couple dirty words in the process, didn't I, babe? She's nodding her head. She knows she's not supposed to talk during these videos. She just loves to hang out. She loves to soak it in. Either that or, for all you know, I'm going crazy and I'm talking to a ghost. Given parallelogram ABCD, I need to prove that AB, that one, is congruent to DC, that one, and AD is congruent to BC. This is one of those types of proofs where you want to look at this and say, well, isn't that the definition of parallelogram? So it's like a two-stepper? No, this is one of those things where we are trying to prove a theorem, and the theorem is parallelograms have opposite sides that are congruent. So we already know this. We just need to prove it. So what do we know? Well, it gives us these little markings here that tell us that they're parallel. So it says parallelogram, so we know that they're parallel. We know that they're parallel. And usually when they give you parallel information, you're thinking alternate interior angle thoughts. So I'm going to do this. I'm going to focus on AB and DC, and I'm going to say that these two guys are congruent because they're alternate interior angles. And I'm also going to say that these two guys are congruent for the same exact reason, alternate interior angles. Now, if I say that, and if I also say that AC is congruent to AC, then I have these two triangles are congruent to each other using ASA. And since ASA tells me that these guys are congruent triangles, that means these sides are congruent and these guys are congruent by CPCTC. Congruent parts of congruent triangles are congruent. No, corresponding parts of congruent triangles are congruent. Tough one. So that's what we're going to do. We're going to say, you guys are congruent, you guys are congruent, you guys are congruent, reflexive. Then we're going to say that the triangles are congruent. And then from there, we can do the proof by using CPCTC, and that should do it. So first things first, always the given. Okay, we are given a parallelogram ABCD, and that's our given. Now, this might be an unnecessary step, but there's no harm in doing it. Since it is a parallelogram, we will say that AB is parallel to DC. AB is parallel to DC. And I'll just say also that AD is parallel to BC. Okay, no harm in saying that. Didn't kill us. I'm still alive. That's the definition of parallelogram. Can I fit it in? I did. Barely. Looks sloppy, but I did. All right, now let's do our angles. Angle BAC. Let's do it in the colors that I gave them to you. Angle BAC. Let's do the measure of angle BAC is equal to the measure of angle BAC DCA. And for the red ones, we'll put it in red. The measure of angle DAC is equal to the measure of angle BCA. Forgot to say the measure of angle. Don't want to be wrong. The measure of angle, what did I say, BCA? And that's the definition of alternate interior angles. All right. So I have two angles and I need the included side. So the included side is literally a side that's being shared. We could say that AC is equal to AC, and that's the reflexive property. Whenever you say something is equal to itself, it's always the reflexive property. Now that I used angle, side, angle, I can say that those triangles, and let's make sure we have it in order. Let's do A, C, D. Triangle A, C, D is congruent to red, purple, so C, A, B. And that is ASA. And since these guys are completely congruent, now we could say AD is congruent to BC, boop, and AD is congruent to BC, so that'll be our last step. Let's see if I can fit that in. AB is congruent to DC, comma, AD is congruent to BC, and that is corresponding parts of congruent triangles are congruent. All right? So again, this is one of those proofs where you're proving an actual theorem. Okay, it's not as simple as you saying, well, my book says theorem 6.12b says that parallelograms have opposite sides that are congruent. So can I just do a two-stepper? Technically, yes, but we wanted to show the actual proof of that, and that's what we did. Dunzo. Given AE is equal to EC, congruent, and DE is congruent to EB, I need to prove that ABCD is a parallelogram. So what do I know? I know that you guys are congruent. I know that you guys are congruent. That's it. I need to explain that these are a parallelogram. Well, there's three ways really that you can show that things are a parallelogram. And none of them really have to do with the diagonals. But what they do have to do with are either opposing angles, consecutive angles, or opposing sides. I'm not given a ton of information about angles, consecutive angles, or anything like that. Consecutive angles would be like this whole angle A and that whole angle D. I'm not given any information about those. Okay, I'm also not given any information about opposing angles, which would be like that whole angle D and that whole angle B. So I'm going to do with the sides thing because I'm given a lot of information about the sides. So I'm thinking that since I'm given two, like the way this picture is set up is I have four triangles. I'm given the fact that these two sides are the same, these two sides are the same, these guys cross in the middle, so I can say that these guys are the same. I can say that, what color didn't I use yet? Red. These guys are the same. So if I can use SAS, 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 and SAS and prove that both pairs of triangles are congruent using SAS, then what I can do is I can prove that AD is congruent to BC and AB is congruent to DC. And I could use CPT, CT, CPP, CT, ICP for that one. Once I've done that, I can say this is a parallelogram. Okay, so let me start over. This is the green and blue is the information I'm given. All right, I could use vertical angles to show that the purples are the same and the reds are the same. Now that I have side angle side 4 times, I could say this triangle, the bottom triangle and the top triangle are the same. The left triangle and the right triangle are the same. And since they're the same, step number 5 or whatever, I could say that AD and BC are the same, and I could say that AB and DC are the same, and I could say that corresponding parts of congruent triangles are congruent. Now that I have information saying that opposing sides are congruent, that is using the opposite sides theorem converse to prove that this is a parallelogram. All right, hopefully I explained that well enough. This is, whenever I make a proof, I always make a rough draft off to the side. So there's my rough draft. So let me start out with my given. Always start out with the given, and that's AE is congruent to EC, and DE is congruent to EB given. All right, so I have two pairs of congruent sides of triangles going on here. I also have the fact that, let me use different colors. Let me use the colors that correspond. I also could say that AED, the measure of angle AED, what a shocking angle, and the measure of angle CEB, the measure of angle CEB, if I can write that correctly, they're congruent. Technically, I didn't need that little congruent thing if I'm saying the measure of angle, but I'm not even going to attempt to erase that. The measure of angle AEB is equal to the measure of angle CED. And this is the definition of vertical angles. Now that I said that, I have a side angle side matches up with a side angle side. So I can explain that triangle, and we have to be careful with the order that we put this in. I'm going to go blue angle, blue, purple, green. So AED, the angle or the triangle AED is congruent to CEB in that order. And I can also say that DEC, the triangle, is congruent to BEA. And the reason for that is side angle side postulate. Since these two triangles, the lefty triangle and the righty triangle, are exactly the same, then we can say that AD is congruent to BC. And we can also say, since these triangles are the same, that AB is congruent to DC. And that was corresponding parts of congruent triangles are congruent. Last but not least, now that we have shown that opposing sides are congruent, we can say that ABCD is a parallelogram. And the reason for that was the opposite sides theorem's converse. Theorem converse. Opposite sides theorem converse, which says that if opposite sides of a quadrilateral are congruent, then you have a parallelogram. Okay? So there you have it. This is a way that you could prove that a quadrilateral is a parallelogram. The opposite sides theorem converse. You have opposite angles theorem converse, which is exactly the same thing, but angles instead of sides. And you have the corresponding sides, angles, I give up. The consecutive angles theorem converse. That one. And those are saying, if they're supplementary, then you have a parallelogram. Fun. Given ADB is congruent to CBD, and also that AD, this guy, is congruent to BC, I need to show that ABCD is a parallelogram. So there's many ways that you can do this. And I did a video where I used what's called the opposite sides theorem converse. I'm going to use a different one, and you'll see which one I do. Okay, because the picture is a little bit friendlier than the other one that I did. What I'm going to do is I have sides that are congruent. I have angle and angle that are congruent, and I have a shape that looks like a quadrilateral cut into two triangles. So what I can do is use the fact that DB and DB are the same exact thing, and I could use SAS to say that this triangle and this triangle are congruent. Okay, one more time, I could use SAS to say that the triangles are congruent. I'm just making a rough draft over here. Once I say that SAS are congruent, what I can do, you know what? No, I'm going to do the opposing sides again. I already know that AD and BC are congruent, but since these triangles are congruent, I could say that these sides are congruent by using CPCTC. So I could say that AB is congruent to DC by using the corresponding parts of congruent triangles are congruent theorem. Now that I have that, I could say that this is a parallelogram using the opposite sides theorem converse. I was going to do the opposite angles one because I was like, let's do this angle and this angle, but I briefly forgot that, I need this whole angle 2 and that whole angle 2, and I really don't feel like saying all right, well, these angles are also congruent, and if I add these angles, I get these angles, and then those are congruent too. I would have to add a few more steps, which I don't feel like doing. I'm a lazy bones. All right, let's write our given first. Angle ADB is congruent to angle CBD. Also, AD is congruent to BC, given. All right. In green here, I can say that side DB is congruent to side DB. And the reason for that is the reflexive property. Whenever you say that something is equal to itself, that's the reflexive property. Now that I have an angle in between two sides, remember the angle has to be in between two sides if you're going to use SAS, but I do have SAS. Now that I have SAS, I can say that triangle, and let's go in order. Let's go from the A and go ADB, triangle ADB is congruent to triangle CBD in that order. And what I did was side angle side, SAS. So since this triangle up on the top left is congruent to that triangle at the bottom right, I could say that AB and DC are the same. So 4 is side AB is congruent to side DC. And that is because corresponding parts of congruent triangles are congruent. Last but not least, these sides are congruent. We were told these sides are congruent. That was part of our given. So opposite sides are congruent. Therefore, ABCD is a parallelogram. And the reason for that is the opposite sides theorem converse. Of course, what the opposite sides theorem converse says is the opposite. If the opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. If for some reason you forgot that that's called the opposite sides theorem converse because that's just a terrible name, then you could say that since opposite sides of this quadrilateral are congruent, then it is a parallelogram. Okay? So there you have it. One more time where we proved that shape is a parallelogram, and we could do that using opposite sides. We could do it using opposite angles, which I thought I wanted to do, but I didn't want to do. There's a way that you could use consecutive angles. If you could show that this whole angle and that whole angle add up to 180, do the same thing with DC. D plus C is 180, C plus B is 180, and B plus A is 180. Then you have yourselves a quadrilateral that's a parallelogram too. You could do that, but it is possible. Maybe not for this one, but that won't happen often. But yeah, this was probably the easiest way to go. Done. Given JI is parallel to KH, so U and U, they're parallel. Great. I need to prove that JGI is similar to KGH. Now, that shape means similar. Similar is different from congruent. Congruent mean they were exactly the same, exactly. Similar means they're the same shape. It's just one's bigger than the other. And there's three proofs or three theorems that we use for this. A means if I could show that two angles are exactly the same, then I have myself similar triangles. And if you're like, why not the third angle? Because if you could show that two angles are the same, then the third angle is going to automatically be the same. Another one is SSS. And you might be thinking, isn't that a congruency one? Yes, it is. But what we're talking about here is ratios. So if I have a triangle with sides A, B, and C, and if I could show that it's congruent, or if the ratio is congruent to sides D, E, and F, then I have myself SSS. The third one is SAS. So if I could show that two sides are proportional, and if I could show that two angles are congruent, then I'm good. So what I'm going to do here is see what I have, see what information I have. I have the fact that JI and KH are parallel. Now that would make J and K congruent because they're corresponding angles. What that also means is H and I are congruent because those are corresponding angles too. So right then and there, I have my double A. Okay, and I can prove that these two guys are similar. So not a lot to show. In fact, this might be only 3 steps, but sometimes with these similar ones, you're not going to show a lot of steps. The similar proofs are a whole lot friendlier than the congruent proofs. So let's start out by saying my given that JI is parallel to KH, and that's my given. That means that the measure of angle GKH is equal to the measure of angle GJI. Also, the measure of angle GHK is equal to the measure of GIJ. G.I. Jane? Nope, close. G.I.J. Ooh, don't make a G.I. Jane joke around Will Smith. He'll slap you. Because of the Oscars. Why is that? That is the definition of corresponding angles. Now, if you have a really mean teacher that doesn't accept double A, which is ridiculous, and they force you to do triple A, AAA, then the third angle would be G is congruent to G using the reflexive property. But like I said, we don't need that because we only need two angles are the same. And so since two angles are the same, we have enough information to say that triangle JGI is similar to triangle KGH. And that is using the double A theorem. Okay? So again, similar proofs are a lot friendlier. They usually take less steps. But we're done. That's how I did it. Given MQ is parallel to OP, so MQ, OP, I need to prove that MNQ is similar to PON. This is similar. Remember, similar is not congruent. It can be, but it's not. Okay, so with congruent, we had like SSS, SAS, ASA, AAS, HL, HA, LL, LA, and you're like, well, which one should I use? Not so many. See, with similarity, we only have three ones that we need to worry about. Showing two angles are congruent, or we could show that the sides are proportional, which means you have three fractions equaling each other, or you could show that two sides are equaling each other as far as proportion goes, and two angles are equaling each other. Now, let's see what I can do here. I have the fact that these guys are parallel. Since they're parallel, I can say that you guys are alternate interior angles, so you're the same. And let's mix it up, because I already did one where I did... No, I didn't. I take it back. Let's just do this. I was going to do vertical angles, but I changed my mind mid-sentence. So because that these are parallel, these alternate interior angles are going to be congruent, and these alternate interior angles are going to be congruent. If you wanted to be like, well, sir, I wanted to do these alternate interior angles and vertical angles, will that work? Sure will, because that follows AA. I'm not given really a whole lot of information about my side, so I'm not going to bother with these guys right here. I'm sticking with AA. So what I'm going to do is I'm going to state my given. I'm going to say that these two guys are congruent by definition of alternate interior angles, and then my last step 3, I could say that they're similar using AA. So number 1 is the given. Side MQ is congruent to side OP, and that's my given. Let's use the right colors. 2, I could say that angle QMP, the measure of angle QMP, is equal to the measure of angle OPM. Also, the measure of MQO is equal to the measure of POQ. And again, my reasoning for that was the definition of alternate interior angles. Oh, these angles are the same? These angles are the same? And all I have to do is prove that they're similar? Then they're similar. M and Q is similar to PON. And that's using AA. And that's it. Given AB over DE equals BC over EF equals AC over DF, I need to prove that these two guys are similar. All right, well, there's 3 ways that you can prove that triangles are similar. Okay, you could use the angle-angle method. If you could show that 2 angles are congruent and 2 more angles are congruent, I could use the angle-angle method. I could also use the SAS method. The SAS method says that if you could show that two sides are proportional to each other, side over side equals side over side, and if you could show that two angles are congruent, then you have SAS. The third option is SSS. And SSS, or if you're a snake, says that if you have a side over a side, corresponding sides, equals a corresponding side equals a corresponding side, then you have similar triangles. And you might look at this and say, doesn't the given tell you pretty much the same thing as this? And I would look at that and say, why, yes. Why, yes, it does. And if you're thinking, so this proof is state your given and then state your proof, and it's only a two-stepper? Yes. Yes, it is. Similarity proofs are not that bad compared to congruent proofs, and this is one of them. This is a two-step proof. That was supposed to be a circle over 1. AB over DE equals BC over EF equals AC over DF given. Oh, look. These proportions equal that proportion, and we're done. ABC is similar to DEF. And that's using SSS. Very, very, very basic. Very, very, very easy. That's it. We're done. Given angle A is congruent to angle B, all right, they correspond maybe. I need to prove that ABE, this whole thing, is congruent to BCD. All right, so there's 3 congruency proofs. Given angle A is congruent to angle B, so these guys, I need to prove that AB is similar to BCD. So similar is a lot friendlier than congruent. Similar, I have 3 main theorems that I can use. If I could show 2 angles are congruent, I'm done. If I could show that 2 sides are proportional, so if I say that side over that side is equal that side over that side, and if I show that 2 angles are congruent, I'm done. Or I could show that that side over that side equals that side over that side equals that side over that side, and then I'm done. I look at this and I see an angle already. So my thinking is, can I do a whole lot with the sides? No. But you know what else I can do? I could show that angle C is congruent to itself using the reflexive property. So if angle C is congruent to itself, and if I have 2 angles already, it's AA. For some reason, I didn't copy and paste the statements and the reasons 2-column proof thingy, so I'm going to do that right now. Statements, reasons. And what I'm going to do is I'm going to state my given. I'm going to say that the measure of angle C is the same as the measure of angle C. And then that's it. That's all I need. And then by AA, these 2 guys are similar. So statement number 1, the measure of angle A is congruent to angle B. Given. 2, let me get the right colors. I could say the measure of angle C is congruent to the measure of angle C, and that's the reflexive property. Anytime you say something is equal to itself, that's the reflexive property. Now that I have these 2 angles and these triangles are the same, and this angle is exactly itself, that's angle. I've done enough. Okay, triangle Abe, rest in peace, Prime Minister of Japan, is similar. Ooh. In being reverential to the deceased, I accidentally screwed that up. ABE is congruent, similar to BCD, and I used AA. Or as the Fonz would say, A from Happy Days. It's a show from like the 70s, I believe. Took us back to when things were happy. Like and subscribe. Given the triangle with vertices A, 4, -1, so right there, B, 5, 6, so right there, and C, 1, 3, given those 3 points, I need to show that triangle ABC is an isosceles and also a right triangle. So this is a proof using coordinate geometry. It's not a 2-column proof. It's not a flow proof or an indirect proof. I am basically using the information that I have to prove what I need to prove. So it's not going to look like the regular proofs that you're used to doing. So I need to show 2 things. Thing number 1, that this is isosceles. Isosceles means that 2 sides are congruent. So according to my picture, it looks like these would be my 2 guys. I also need to show that this is a right triangle. So according to my picture, that's the guy that would look right. So the 2 things that I need to show are that BC and CA are congruent. Since these are coordinates, I'm going to use the distance formula. The second thing I need to show is that this is a 90-degree angle. So what I'm going to do is find the slope for BC and the slope for AC and prove that they're perpendicular. Okay? And I'm going to do that again using 2 main steps. So depending on what type of teacher you have, you may need to restate the given, but I don't have to. If I was your teacher, I would just ask you to show what you need to show and explain what you're doing. So I would want you to say something to the effect of, well, number 1, and I'm showing this part first, we need to show that BC or CB is equal to AC or CA. Okay, I probably said it backwards at some point, but it all means the same thing. Now, this is coordinate geometry. So what we need to do is use the distance formula to find the length of each of these lines. And this is going to be the distance formula. Okay, x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared, all of that in a big square root. So it doesn't matter which one. I'll show BC first. So I will explain that BC, I need to find the distance, and the distance is a big square root. Okay, let's say that B is our 2's and C is our 1's. So if I'm doing x sub 2 minus x sub 1, that is an x. So 5 minus 1. So 5 minus 1 squared plus 6 minus 3 squared. Okay, that's going to get me 4 squared, which is a fun game, plus 3 squared in square root. Still in the square root, 16 plus 9, which is the square root of 25, which is 5. So the length of BC is 5. Now I'm going to show that AC is 5. Or what did I call it? Yep, I called it AC. So AC, the distance, is going to use the distance formula again. So let's call you my 2's and you my 1's. So let's do 4 minus 1 squared, 4 minus 1 squared, plus -1 minus 3 squared. That's going to equal 3 squared plus -4 squared. 3 squared is 9. -4 in parentheses squared is 16. Looking familiar? That's going to equal 25 in the square root. And the square root of 25 is 5. Okay? So distance formula out. So I will say, because I almost stopped right there. So I will say, so BC is equal to AC using the distance formula. Might be saying too much, but why not? Why the heck not? This one won't take as long. I could use the slope formula, but I'm just going to say we need to show that BC is perpendicular to AC. I have all this space, so I'm going to use it. Slope of BC is, now let's go up here. Let's find the slope. Up 1, 2, 3 over 1, 2, 3, 4, 3 over 4. And AC is down 1, 2, 3, 4, 1, 2, 3. So negative 3 over 4. The slopes are negative reciprocals. Okay, 3 over 4. Oh, wait a minute. This is supposed to be 4 over 3. Almost ruined the whole thing. The slopes are negative reciprocals, so BC is perpendicular to AC. Since BC is equal to AC and what was the other thing? BC is perpendicular to AC. Triangle ABC is an isosceles right triangle. Ran out of space there. Okay? Probably could have written out right, but it's too late. So there you have it. Kind of a mess, but and I almost screwed things up really badly over there. But that's how it's done. You basically just show whatever math you need to show to make sure that that works. And that's it. We did it. The vertices of quadrilateral KAIT are K, which is 0, 0, A, which is A0, I, which is A plus BC, and T, which is BC. Use coordinate geometry to prove that quadrilateral KAIT is a parallelogram. Well, there's several ways that you could prove something is a parallelogram, but probably the easiest way to do it is to show that you have two opposite sides are congruent. Two pairs of opposite sides are congruent. So if I were to imagine KA and IT, so that's kind of what I have to do. I have to do that. I have to show two pairs of opposite sides are congruent. So number one, I have to show that KA is congruent to IT. When I'm done that, I have to do AI and KT are congruent. Okay, so again, if you're like, I don't see it, I don't see the picture. Look, there's a picture, KAIT. It has to give you whatever order it's in. So I have to show KA and IT, and then I have to show AI and KT. That's what I have to do. So that's what I'm going to do. Okay? So I need to show that KA and IT are congruent. So the way we do that is we use the distance formula. Okay, so let's write out the distance formula down here. The distance formula is x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. All right, so if I were looking at KA, okay, we'll do this all in separate parts. KA, I would say that the distance equals Let's let u be x sub 2, y sub 2. And let's let u be x sub 1, y sub 1. In fact, I'll write that out just once. I'll do this once, and then I probably won't write it out again because otherwise it'll get sloppy. 1, 1, 1, 1. You're supposed to be 1. All right, x sub 2 minus x sub 1 is going to be a minus 0. A minus 0 squared plus 0 minus 0, which is 0 squared. So let me get rid of this extra. Okay. That gets me a minus 0 squared. So I need my square root still. I don't know why I got rid of my square root. So square root a minus 0 is just going to be a squared plus 0 squared is just 0. So the square root of a squared is just a. So the distance of Ka is just a. All right, I can handle that. So the distance of it has to be a as well. So it, distance formula. Okay, let's let u be our 2's and u be our 1's. So x sub 2 minus x sub 1 is going to be b minus a plus b. B minus, now be careful. If I'm subtracting both a and b, it's going to be a minus b. I know that looks weird, but trust me. Plus c minus c, which is 0, so 0 squared. B minus b cancels out, giving me a squared. Plus 0 is just a squared. And again, the square root of a squared is a. So we did it. So since Ka is a and it is a, Ka is it. Thing number 1 proved. Now, Ka is it. Now I need to show ai is kt. So I'm going to say show ai is kt. AI, artificial intelligence, or Allen Iverson, my second favorite Sixer of all time. All right, AI. Let's get rid of all this mess up here. I'm looking at AI, so let's let u be the 1's and u be the 2's. So x sub 2 is a plus b minus x sub 1 is a squared plus c minus 0, which is just c squared. A minus a cancel out, and that gives me just b squared plus c squared. Now let's not try to simplify that, because my goal is to make sure that kt is the same thing. So who cares if it's simplified? Who cares? Kt, that distance, big square root. So let's let u be my 2's and u be my 1's. So I have a feeling this one's going to be a lot friendlier because of that double 0. B minus 0 plus c minus 0 is going to be b minus 0 is just b, so b squared. And c minus 0 is c, so c squared. So we just showed that AI is KT, which means Kate is a parallelogram. And I believe the name of that theorem is the opposite sides something. I don't know. But since two pairs of opposite sides are congruent, it's going to be parallel. And there's a name to that theorem. It's escaping me because right now I'm recording this at 10:15 p.m. But that's how you do it. We proved it. All right. Coordinate geometry proofs. You just have to do the math. And a lot of times the math is fun because things disappear. That's what happened. Fun, 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 fun. The vertices of quadrilateral coat are C00, so let's just get these down. O50, O, A, which is 52, and T, which is 0, 2. Prove that coat is a rectangle. All right, so I have this picture here. Let me use a different color. I have this picture. In order for something to be a rectangle, all right, we need to show two main things. Thing number one, we need to show opposite sides are congruent. And thing number two, we need to show that all four angles are 90 degrees. Okay? Now, since we have a picture here, and since this is a rectangle and all of the measurements are super nice, we do not need to go crazy whipping out distance formula, or we don't have to go crazy whipping out slope formula. Okay, what I have to do is I just need to show that TA and CO are congruent. Then I need to show TC and AO are congruent. So let's do that first. Okay, let's do that first. And I'll say that. We need to show that TA equals CO, and we need to show that CT, or TC, I think I called it, is equal to AO. Okay, so let's do that. Pretty easy because everything lines up perfectly. TA is 1, 2, 3, 4, 5 units. So TA is 5. CO is 5. So TA is CO. Okay? If these lines weren't so pretty, I'd have to use the distance formula. I did that in previous videos, so if you want to go back and watch, I beg you. Also, TC 2, AO, which is what I do when I'm hollering out my friend, that's also 2, which means TC equals AO. So, opposite sides are congruent. Okay? What I'm going to do to show that these are 90-degree angles is I'm going to say what the slope of TA is, the slope of AO is, the slope of CO is, and the slope of TC is, and prove that all of these guys are parallel to each other because of negative reciprocals. So TA, let's actually word it better. The slope of TA, or let's do this. Let's be creative. MTA, that means the slope of TA is 0 because it's a perfect horizontal line. The slope of AO, which is what I do when I holler out to my friend, is undefined. The slope of CO is 0. And the slope of TC is undefined. What that means is TA is perpendicular to AO. AO, which is what I say when I'm hollering out to my friends, is perpendicular to CO. CO is perpendicular to TC, and TC is perpendicular to TA. So all angles are 90 degrees. Opposite sides are parallel or are congruent. All angles are 90 degrees. Therefore, coat is a rectangle. All right, so that's coordinate geometry proof. You're just proving what you need to prove to explain yourself. You're not making two columns. You're not flowing. Unless you're making a rap out of this, which all of those AOs sure sounded like I was flowing. Like and subscribe. Triangle art has vertices AB, which is A, R is A plus CB, and T is A plus C over 2, B plus D. Use coordinate geometry to prove that triangle art is isosceles. So something that is isosceles is going to have two sides that are congruent. And since I'm given letters instead of actual things to graph, I have to use the distance formula a bunch of times. So a little reminder that the distance formula is x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared, all in a square root. Comes from the Pythagorean theorem. So let's see if I hit gold. I'm going to find the difference of A, or the distance of AR. I have to find the distance of RT, and then maybe I have to find the distance of AT. And I'm going to say that. I'm going to say, and I don't even, well, yeah, I'm still going to write out my steps. We need to show that two sides are congruent. So I need to find AR, I need to find AT, and I need to find RT, and hopefully the ones that I choose strike gold. So let's start out with AR. AR is going to give me a distance of big square root. Let's call you my x sub 1s. Let's call you my x sub 2s. So x sub 2 would be A plus C minus my x sub 1, which would be A. Things disappear, squared. Plus B minus B. How convenient. 0 squared. Okay? The A's cancel out. So this just becomes C squared plus nothing is just C squared. The square root of that, C. Okay? Okay. Let's try AT. I don't have a good feeling about it at all. AT is going to be D equals probably a bigger square root. Let's do that. Let's let that be my x sub 2, x sub 1. So A plus C over 2 minus A squared plus B plus D minus B. So B plus D minus B squared. Let's bring that root over. You go away. You go away. So that ends up being C squared, C over 2 squared, which is C squared over 4 plus just D squared. Let's leave it like that because it's not going to simplify any further. There's no tricks to find the square root of a sum. So let's leave it like that. Obviously, AR and AT are not the same. So I'm guessing that RT is going to be the same as AT. And if it's not, then it better be the same as AR. Otherwise, I wasted my time. So let's find RT. Retweet. Twitter, a dying platform. All right. The distance, let's let that again be my 2's, that be my 1's. So you're going to be A plus C over 2 minus, now be careful, I'm subtracting both A and C. So minus A minus C, close that, squared. Plus, I'm going to need more space on this one. B plus D minus B squared. You go away. You go away. All right. So this is going to be a tricky one. You ready? Maybe, maybe not. We'll see. What I have to do with this guy is combine the C over 2 minus C. And what I'm going to do is I'm going to turn this C into 2C over 2 so I can combine like terms. So minus regular C over 2 minus 2C over 2, close it, square it. You just become D squared, so all is well with that one. Okay, now I can combine these fractions. Okay, C minus 2C is negative C. 2 over 2 stays 2. That lives inside of a parentheses, squared, and you're still plus D squared. Negative C over 2 times itself is C squared over 4 positive plus D squared. If you're the praying type, you're saying right now, praise the Lord. Because AT equals RT, which means ART is isosceles. I got really nervous starting this problem out, but we know that this is isosceles. We just have to make sure that our math proves it. And that's what we did. And so we wasted our time doing ARs, but aren't ARs a waste of time anyway? Oops, a political comment. Don't like and subscribe, I guess. Please do like and subscribe. Prove ABCD is an isosceles trapezoid. In order for something to be an isosceles trapezoid, you need to show two things. You need to show that these two sides are parallel, and you need to show that these two sides are congruent. So what I'm going to do is I'm going to find the slope of BC and the slope of AD and show that they're the same. Then I'm going to show the distance of BA and the distance of CD and prove that they're the same. Therefore, it's an isosceles trapezoid. Let's write out a few friendly reminders. The slope formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That's going to come in handy for the whole parallel thing. The distance formula is a big square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Okay, so let's start out by doing the whole parallel thing. And I'm going to say that I need to show that BC is parallel to AD. So let's say the slope of BC, I'm going to use the slope formula. Let's let this be x sub 1, y sub 1. Let's let this be x sub 2, y sub 2. So y sub 2 minus y sub 1 is c minus c. I think I can handle that. Then I have x sub 2 minus x sub 1 is going to be b minus negative b. Double negative makes it positive. 0 over 2b is just 0. Makes sense because that looked flat to me. Now let's find the slope of AD. A similar thing should happen. If I call u x sub 2, y sub 2, and a x sub 1, y sub 1, then I'm going to do 0 minus 0, another toughie, over a minus negative a. Oh, look, a double negative. Let's make it a positive. 0 minus 0 is 0, over 2a is 0 again. So, since the slopes are the same, I have now proven that BC is parallel to AD. Okay? So that was thing number 1. Thing number 2 is I need to show that these two guys are equal in distance. So I'm going to use the distance formula to show that AB or BA is equal to CD. Compact disc, those of you 90s kids. D is equal, and let's rewrite it out so that I'm a little bit more specific. Let's start out with BA and show that the distance of BA is a big square root of, let's let you be my 2's and you be my 1's. So negative b minus negative a squared, negative b minus negative a squared, plus c minus 0 squared. Double negative makes a positive. Now, since space is an issue and time is money, okay, I'm going to use the idea of perfect square trinomials for this one, and I'm going to make sure that I understand that this becomes b squared minus 2ab plus a squared, and u are going to be c minus 0, which is just c, so plus c squared. If you're like, whoa, 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 what did he just do there? Perfect square trinomials. I'm not going to go any further than that because I know that when I do CD, that it's going to end up looking like the same exact thing underneath the square root. So what's the point of trying to clean it up? Okay, what's the point of trying to combine terms and simplify it? You probably can anyway. Let's keep that red going. CD. The distance for that, big square root again. I'm going to let you be my 2's, let you be my 1's. That is going to be c minus 0 squared. Oh, I did it backwards, didn't I? Doesn't really matter. Plus b minus a squared. C minus 0 squared is c squared, so there's my c squared. B minus a squared using perfect square trinomials is going to be b squared minus 2ab plus a squared. So there it is, the same exact thing. So, and let's get rid of these rules because I won't need them anymore, even though they look so darling. I just showed that BA and CD are the same. So let me say that. So since BC is parallel to AD, and since BA is equal to CD, that tells me that ABCD is an isosceles trapezoid. All right, so that's coordinate geometry. You're not setting up a two-column proof. All right, you're just showing the math that you need to show to prove that these guys are exactly what they say they are. Fun.